Welcome to this video on FMRI group analysis. My name is Mark Jenkinson and I'm going to be talking about different aspects that we do when we're actually trying to analyse a group of different subjects. It's still going to use the GLM, which you'll be familiar with from single subject analysis. In fact, the GLM is what we use for all kinds of neuroimaging studies in order to do statistics. In this talk, I'll be concentrating on the aspects which are relevant for doing analysis of groups of individuals for task FMRI. But many of the things that we'll talk about are also general for other situations where we're doing group analysis with a GLM. So let's consider first of all the sort of context that we might be in. So in a task FMRI experiment, we would often have different subjects, we would often have them in different groups, and sometimes we would even have different sessions for each subject. So that gives us many different layers or levels that we could look at. We can look at what's happening within an individual session. We can look at what happens across different sessions for one particular subject. We can look at what's happening within a group, or we can look at what's happening as the difference between two different groups. And so we need tools for enabling us to look at these different options. And that's what we're going to cover here. Let's, however, start more simply. So let's consider one group where we've got a set of different subjects and each of them has a single session. That is, they've been in the scanner once and they've had one particular run of FMRI. If we do analysis of that single session for that particular subject, so the first subject happens to be Mark in this case, then we can look at a particular location in the brain, what is the effect size? That's effectively the beta that we were getting, or the parameter estimate, our PE. We can see how large that is, and that's reflecting how strong the activation was, because it is reflecting the size of the fitted amplitude that we had of our predicted response to the actual data that we recorded. So that's an indication of how strong the response was to the stimulus that we were providing. So we have one measurement that we've got from that particular subject, and we've got that through using our first level GLM. So in this case, Y was the data that we recorded from the scanner. X is our design matrix, which encoded our predicted responses, so the combination of the HRF with our stimulus timings. The betas were the fitted amplitudes that we had, and then the epsilon was the residual noise. There's a K subscript across all of this because actually it'll be a different design matrix, as in different data and potentially different design matrices, certainly a different GLM for each of the individuals within the group. So in this case, K is equal to 1, because we're looking at the first subject. And so this effect size is this beta value that we're talking about. And also we have this residual noise, which also allows us to consider what is the variance that we have. So we have both an estimate of the beta, but we also have an estimate of the variance of beta. So you've seen that before, and we get statistics from that. Now we can look across all of the individuals in our group. We can do that for all of them. So here I'm showing them each one on a different line. I'm just stacking the lines up vertically. That axis doesn't have any meaning really, it's just the subject number. What we're interested in is how far along the x-axis, the horizontal axis, are the particular effect sizes, and what is the width about their uncertainty that we get from our epsilon values. And even at this point, in such a simple example, and we've got two different options for what kind of questions we can ask about what's happening in this group. We can ask a fixed effects question, or we can ask a mixed effects question. And these are different in terms of what are we trying to infer. Are we trying to just talk about what's happening on average within this particular group of individuals? Or are we trying to say what would happen on average in the population if we actually extracted any group of individuals, not these 6 particular people? So we'll unpack that a little bit more. In fixed effects analysis, we are really looking at these exact 6 subjects. And everything that we're going to say about their average is going to only be true for these 6 subjects. We're not in any way trying to go beyond those. So maybe they are, the 6 richest people in the world, and we're interested in what's true for just these people that have, vast amounts of money. But it's not a common thing that we would do. And it really does only tell you about what's happening for these 6 individuals, and it doesn't tell you about what's happening for anybody else. So in order to do the fixed effects analysis, we would take our average of these 6 particular values, which we can do in this way. And in this way, I'm creating a new beta, and this is my group beta. So this is simply the mean value in this case. And what we have now is a second level GLM. It's actually a really simple equation. All we've basically got is we are calculating a group mean from our different beta values. So here we've got the 6 beta values, which are represented by the stars. And we're saying, how do we calculate our group mean from that? And actually we can do that as a design matrix. So we can implement that equation that you can see in the bottom right in terms of a design matrix. If we just make this as the design matrix, we just put ones in all of down in a single column, then that is actually going to calculate the average. And that's useful to know. Whenever you see a design matrix and there's just a column of ones, or even just part of that column is ones and the rest is zeros, it's going to be calculating the average of whatever is along that, whatever has a 1 associated with it. So in this case, it's the average of everything. If we'd had some zeros in it, it would be ignoring the ones with zeros. So that's useful to know because we're going to use that again and again. And that's how we can calculate a group mean using this kind of GLM equation. And so the fixed effects analysis has 2 different levels. We've done an analysis of the MRI data at the first level, that's what the Y was. And then at the second level, we've just taken the average of all of the effect sizes that we found from our first level GLMs. But it only really considers these 6 subjects. So maybe there were 6 subjects which had the rarest disease, ever, and there were only 6 cases in existence. In that case, it's just telling us what's happening about these 6 individuals with this particular rare condition. And that might be something that happens. Probably not. Generally, we're not so interested in that particular question. But occasionally we're forced into it. And so it's something that you need to know about. So fixed effects, just estimates the mean across these subjects, and the only variance that we're considering is the within subject variance. That is, what is our uncertainty on each of the little betas as a consequence of the noise in the MRI data. So we're only considering variance associated with the fact that our MRI data was noisy, and that gives us some uncertainty on our values. So that's what fixed effects is. Mixed effects is different. Here, we have the same first level design happening, we have the same estimates. But now we're not only just interested in the mean value, we're also interested in the variance around that mean value, because that captures the fact that we have some variability between subjects, and the fact that if we took a different set of 6 subjects from a population, from a wide population, then we would not get these exact 6 values again. We'd get something different. And how different that would be is controlled by, or is estimated by, how different the particular sample that we've got is. So there is some population spread of what we would expect to see for activations in each individual. Even if we had absolutely perfect measurements, we'd still expect to see that each individual would have a different level of activation based on all sorts of characteristics of their biology. And so if we want to capture that information and include that, then we need to have this second variance component, which is our between subject variance. And so that is incorporated in our second level GLM. So you've seen the first part of this already from the fixed effects example. Now we have an extra thing that we're estimating, which is the residual, or the difference, the variance that we have around the mean value for our particular effect sizes. We would use exactly the same design matrix because this beta G is the same thing. It's still the mean of these 6 values in this case, but we are interested also now in this other variance. So we have a population mean, and we have now a between subject variation that we're measuring from that GLM. And of course now our GLMs look more similar. They are more balanced. We have, both of them have a variance part, and that's why it's mixed effects, because actually what we see in terms of the variability of our parameters is controlled by both sets of variances. So the two variances are put together, they're mixed. Whereas in fixed effects, we don't consider what happens at that second level. We only consider the variance from the first level. And the most important thing here is that mixed effects allows us to then generalize to a wider population. The result, the statistical result we get from a mixed effects analysis is true in general. If we'd taken another 6 individuals from that population, then we would expect the same result. And that's really what it's useful for. It's useful for taking into account the fact that, okay, these 6 individuals are maybe not the most unique individuals on the planet. They just happen to come from a particular population. Maybe they were rich people, maybe they had a particular disease, but they're not the only people in that category. And if we had drawn another sample of people from that category, we'd expect a different result, but mixed effects takes that into account. And so when we're doing the statistics, it will only give us a significant result if that is likely to be true for all samples from that population. So we estimate the mean across the population, we estimate the between subject variance to account for that thing. And that's why we can then make that inference to the wider population. So hence mixed effects is almost always what we want to do. We're pretty much always interested in what is true for the population that our subjects have been drawn from, not just for those particular subjects. So we very rarely want to look at fixed effects. Mixed effects is really what we want to do at. Well, there is one example where fixed effects will actually be something that we need to look at, and we will get to that in one of the other talks. So now back to the more general example, where we've got different groups, we've got potentially different sessions. If we want to sort of analyze this, there are multiple different ways that we can analyze it. One way is that we could put everything in together. We could throw all of the MRI data into one huge matrix, and we could analyze everything and set up a design matrix which encoded everything which we have here. But that's not so great, because it's hard to then figure out how to set everything up properly. It's very computationally demanding by comparison with other options. And whenever we added something or we took something away, we'd have to reprocess everything. So instead of the all-in-one approach, we generally use the summary statistics approach, and that simply breaks everything down. And so this is already what you've seen. We do individual sessions on their own to start with. So we're looking at one run in the FMRI. So often that's the only one that you would have for a particular subject. So often we don't have multiple sessions per subject, and we would collapse that, but you might. If you do have multiple sessions, you would analyze each session on its own, and then you would combine them across subjects. But maybe you've only got one per subject, but you still might have a group, and you are still then looking at combining across a group. And as we saw in the previous slides, we can actually have different GLMs at different levels, and that allows us to split things up. And it's a much easier way to understand it and to set things up, and it's a more efficient way of doing the computation. And actually, we've been very careful to make sure that it's exactly equivalent to setting up the huge matrix of the all-in-one approach. So these will give you exactly the same results, but there's a lot of benefit by doing it in this particular way. And one of the important things to understand about this is that it needs to pass information between each of the levels. So obviously we saw before, if we were going to do a group analysis even for a single group, then we needed to know the effect sizes from the first level GLM in order to do the second level GLM. And that's generally what we do. We pass up information from one level to the other. And the information that we need to pass up is actually the COPE. So I talked about effect sizes before, but it's actually the contrast of parameter estimates that we're most interested in. So we're going to form contrasts at our first level. Those contrasts might be very simple. They might just pick out one of the parameter estimates, or they might do something more complicated. But we're going to use those contrasts, whatever they are, and we're going to pass those up as well as the variance of those and the degrees of freedom appropriate for that. And they are the three things which get passed up. We do not pass up the statistics directly, because actually we need to combine them in different ways when we get to the different levels. And so we need to actually pass the COPEs, which are like the betas, And so you saw before we were taking betas from one level and using them in the second level. If our copes were very simple now, we're just picking out individual betas, that's exactly what this would do. But we can also combine betas together and look at those combinations when we go up. So maybe we're taking the difference between two different conditions at the first level, and then we're looking at the average of that difference at the second level. That's a very common thing that we would do. And so when you are doing your analysis, you'll see that these are the things which get saved and these are the things which get passed between different levels. The copes, the var copes, and the degrees of freedom. So this is the way that we analyse multi-level experiments. And the tool that we use for that in FSL is called Flame. There are actually a couple of different options within Flame that you can use. So the default is that we would use Flame 1, and that's a fast approximation that works well. We would generally recommend that. It is really quite accurate, but there is also an optionally slower and slightly more accurate approach for when you really care about very precise values, and that's Flame 1 plus 2. And what that's going to do is it's going to look at the results from Flame 1, and if they're a long way away from our statistical threshold, it just leaves them the same, because the second option here is a very small refinement. But for voxels which are very close to the threshold, that might be enough to take them over the threshold or actually to take them back under the threshold. And so Flame 2 is only run for those voxels where they are already close to the threshold. It uses a technique called MCMC. You don't need to know anything about that except for the fact that it's really slow. And so that's the reason that this is something that you would only do at the end when you think that you've got values which are quite close to the threshold. We would generally recommend it, do your analyses, get everything right. Once you're ready to sort of write up your paper, then actually do the Flame 2 just to check that nothing really changes. Typically it's a very small change, but you could be in a situation where things were ever so close to the threshold and that would actually change the nature of your results. So it is worth doing that just at the point where you've finalized everything. There are different options that you can do when you're looking at the feat GUI within FSL in terms of how to do the higher level analysis. So we talked about Flame 1 and Flame 1 plus 2, which are the third and fourth options here. There are a couple of others. Fixed effects we've talked about before. Generally you would not be using it. There is one particular case which we will get to in a different talk, but generally we want to use mixed effects because we want things to be generalizable to the population. So you'll see that options 2, 3 and 4 are all mixed effects. Option 2 is a thing called ordinary least squares, or OLS, and that is different from Flame in several different ways. So one of them is that actually Flame allows us to have different variances for different groups. So if we have a patient group and a control group, and we think the patient group might be more variable in terms of how they're responding to a particular task, if it's task FMRI, or this is also true in other situations, then having a different variance for that group can be helpful if there's a wide range, say, of disability or cognitive ability within that group. That can capture actually that data better. So that's one of the things that Flame can do that OLS can't. So OLS has to have the same variance for both groups. We can also have non-balanced designs, and that simply means that the design matrix itself is different in different subjects. And OLS has to have the same design matrix, whereas actually this is very helpful for us in many experiments, such as learning experiments, where it's definitely going to be different in different subjects. They're going to make different errors, and hence what we're going to encode in different columns of the design matrix would be different for different subjects. So that's something, non-balanced designs is a crucial thing that we need. So don't use the OLS option because of that. And also because unequal group sizes are a problem for OLS, whereas actually for Flame, everything is fine. You can have different group sizes and that will be taken care of automatically by all of the statistics. You'll get valid results. And there's also a thing called the negative variance problem. And we talked about mixed variance, and mixed effects, and the fact that you've got a couple of sources of variance. OLS simply tries to estimate the combined variance. But it's possible that that estimate of the combined variance, which is just an estimate, might be actually less than the first level variance. And that's just not possible because variances always add. So the only way that that would be true is if the between subject variance part was actually negative. And so that's why it's called the negative variance problem. you can't end up with a combined variance being less than either of the two constituents. And our first level variance we normally have quite a good handle on because we've got lots of data from our MRI. We've got lots of different images. And so if you look at the results from FLAME versus OLS, there are two different things which could happen. You could end up with more statistically significant results in FLAME rather than OLS because of the fact that actually it's better at adapting to different heterogeneity, so whether it's different variances in different groups or the fact that you've got different design matrices, that's a very beneficial thing for FLAME, whereas actually the opposite could also happen. You could also end up with less activation. That would generally be because you've got rid of the false activations, which OLS is showing due to the negative variance problem. So the estimates of the variances are quite difficult to get with low subject numbers. And this is one of the problems which can plague OLS, particularly when it's not used with a lot of subjects. In general, our recommendation is strongly to use FLAME and not to use the OLS option. And this is just giving you some reasons why. Talked a little bit before about multiple group variances. I want to talk a little bit more about that because there are some details which are useful to understand. So if you want to be able to do separate variances for different groups, there are some restrictions that we still have within FLAME, so we can't do it in all cases. And one of the things that you should be aware of is not particularly associated with FLAME, but it's still a restriction, which is that estimating variance is difficult to do on low numbers. And you shouldn't separate variances if you have a small number of individuals in your different groups. So I would say as a rule of thumb, if you don't have 20 subjects in each group, you shouldn't be doing separate variances. And in fact, a pooled variance, although it won't be different for the different groups, will still be better because it will be a more accurate variance estimation and you'll benefit from having less uncertainty of that, even though you're pooling it across the two. So if you've got a small number, particularly if you've got less than 20 subjects in any of your groups, then I would not separate group variances. You don't need to separate group variances in many cases, and I think you should have a good reason before separating group variances. But if you do know that you've got a very variable group, such as a group of patients which have different cognitive abilities, then it can be useful. If that is the case, and you want to be able to separate it, then you have to know that some design matrices are okay and some are not. So the valid design matrices are the ones which are separable. And by that, I mean that actually you don't have non-zero values in a column running across two different groups. So in the examples that we've got at the bottom here, the first column represents our coding for the variance group. So variance group 1 for the first three, and then variance group 2 for the second three. The other two columns are EVs. And in this valid case, the non-zero values are only associated with one of the groups. So it's either associated with group 1 or with group 2. They never span more than one group. In the invalid case, we have this EV, which has non-zero values across two different groups, and that's not okay. In fact, we have both of them. In other situations, if we had the same variance, those two design matrices, those two sets of EVs would give you exactly equivalent results if you had appropriate contrasts. But when we're separating group variances, we can only do the valid case. We can't do the invalid case. So it's necessary for you to actually set up your design matrix in an appropriate way. So in summary, we've looked at fixed effects analyses, which give you results for this very specific sample, the particular individuals which you've managed to scan. And that's normally not that interesting. What we would want to do normally is mixed effects, because mixed effects analyses give you results which generalize to the whole population, or at least to the group that you have sampled from. So if it's a patient group, it generalizes to all patients which would fit your particular criteria. The summary statistics approach allows us to do analyses at different levels and then pass them up. So we do individual analyses of each FMRI run that we have, each FMRI session, and then if we have multiple sessions for each subject, we combine them together, but often we just have one session for each subject, and then we would look at the higher level, combining across subjects in different groups. It's going to pass up the COPE, the contrast of the parameter estimates, the variance of that, and information about degrees of freedom. And we use the GLM at every level. So we're doing everything with the GLM. We have a GLM at the first level, which is looking across time and how things vary there. And then we have a GLM at the second level where we've got different subjects and we're looking at how that changes. We do our higher level analyses with Flame within FSL, and that can cope with a range of things such as unbalanced designs where the design matrix is different for each subject, unequal group sizes, and also is not perturbed by this negative variance problem that solves that. Multiple variances can also be modelled, but there are some constraints. You should have a good justification for why you want to model different variances. You need a decent number of subjects, and you need to make sure that your design matrix breaks down in the right way. But if you have that, then it can be a useful tool, but it's not necessary. You can also just have a pooled variance and have everybody in one group.